Okay, thank you, George. And thank you for having me here. I've had a very fun day talking to colleagues in various buildings today, but it's been a full day, and I've certainly learned a lot. And I hope to pay some of that back to you now by talking to you about the research that I've been doing, divinating the dark matter content of dwarf galaxies. But let me frame my goal in terms of one thing, really, which is one theme, which is to use astronomical observations to learn something, anything, about the microscopic nature of dark matter. And by microscopic, I merely mean something that's on scales smaller than we're looking at astronomically. And just doing that would represent a major step forward right now. So that could go several different ways. One thing I won't say much about, or I don't plan to say much about, but I'm certainly happy to take questions about it, is looking for astronomical evidence of particle interactions involving the dark matter. One way this might go is to see gamma rays coming from regions of high dark matter density due to dark matter annihilation. And I won't say anything about that except to note that there are at present searches ongoing for that. There are some tantalizing hints of signals, but nothing that's clearly convincingly a signature of dark matter annihilation. What I will focus on are basically the traditional way of studying dark matter through its gravitational interactions, in particular using dynamics of galaxies to make inferences about what I then call the dynamical masses of galaxies. And once you subtract away the masses of the things you can see, what you're left with is what I define to be dark matter, the difference between dynamical and luminous mass. And the way this goes is basically, it's a hypothesis test. I think what we have in cosmology is a null hypothesis regarding the microscopic nature of dark matter, which is a hypothesis that says very little or even nothing about the microscopic nature of dark matter other than it doesn't matter for structure formation. So in lambda CDM, that is a minimal hypothesis regarding the nature of dark matter in that we ascribe to it only a gravitational interaction, and we suppose that the dark matter particle is sufficiently sluggish that it has a negligibly small free streaming scale, so that doesn't matter for the purpose of forming an evolving structure in the universe. And that gets us quite a long ways. That simple idea is good enough to understand just about everything we see in the cosmic microwave background, the large-scale structure and evolution of galaxies. Where it starts to become interesting, though, is on small scales, because small scales is where microscopic properties of a dark matter particle might ultimately manifest. So there are people here who study the small-scale structure at high redshift, including George and the structure in the Lyman alpha forest, and that's getting at the ability of dark matter to cluster at small scales at high redshift, and some limitations on that may be, in fact, due to the nature of the dark matter itself. But going closer to home, literally, in terms of the Milky Way and its environment, and even galactic scales, it's not clear that this minimal picture of dark matter is giving us a viable description of what we see. So the inference process will be to rely on cosmological simulations that assume this null hypothesis of minimal dark matter, see what structures form in those simulations, then compare to what we see and see if we can come up with a discrepancy that would require a change to the dark matter properties put into the simulations. So most of what I'll talk about has to do with this kind of comparison between a high-resolution in-body simulation of dark matter structure growth, that's represented on the left in this now 10-year-old simulation called Aquarius. And what you're seeing there is color-coded according to the density of dark matter. So brighter regions are regions of higher dark matter particle density in this simulation. And the box here is representing something that's the environment of the Milky Way. So if you could see stars in this image, the Milky Way would be sitting right here. The spiral arms would be about this extent. But this is showing the rich dark matter scaffolding against which the stellar structure, on which the stellar structure is built. And what you're seeing here, because this is the cold dark matter picture and there's no small scale limit to structure formation, at least within the resolution limit here, you're seeing all kinds of small scale structure in the form of sub-halos around the Milky Way halo. If you could zoom in on those, you would see sub-sub-halos, and so on, down to certainly below the resolution limit of this simulation. So we could take that as some first-order prediction of the cold dark matter model. On the right, I'm showing observational data, and this is something that's also, you could think of it as something that's representing the Milky Way. This is Andromeda as seen in stars. This is a very deep image, so that the galaxy itself is overexposed in the center, the spiral arms region. But you're seeing the environment around Andromeda, and conveniently circled in the green circles are these dots that are detected dwarf galaxies that are orbiting Andromeda and inferred via means I'll talk about to contain large dark matter components. And the first thing you might notice about these two images is that there's vastly different amounts of substructure, many more dark matter subhalos predicted to be around the Milky Way than we see as luminous galaxies. That shouldn't be all that surprising in that we're talking about stars in one case and dark matter in the other. So this, while it's been referred to as the missing satellites problem for a couple of decades now, to my mind, this merely invites theories about how you form galaxies within low-mass dark matter halos. Where things get interesting, I think, is when you combine that kind of picture with looking at the internal structures of dark matter halos. So the same simulations can have many dark matter particles per subhalo, and you can go in and examine the dark matter density as a function of position, distance from the center of these halos, and generations of n-body simulations have now showed that there's a characteristic, oh, it's over here, a characteristic dark matter density profile here. You've got very dense inner region falling off here, but really this is well characterized by a split power law. Analytically, you're seeing this. I might call this the NFW profile after Navarro Frank White, who first wrote it down 20 years ago. But it's a split power law. At some scale radius, there's a transition from a relatively shallow inner slope to a steeper outer slope. But what I'll focus on today is this inner behavior, where as you go in the limit of small radius, the density diverges as 1 over r. That's referred to as the NFW cusp that characterizes cold dark matter halos. And that's then something we can go check observationally. And it's interesting to do so because there are alternative dark matter models at the particle level that make different predictions about this behavior. So here are some simulated dark matter density profiles in which the simulations put in a self-interaction, a non-gravitational self-interaction between the dark matter particles. And in regions of high density, such as that original NFW cusp, particles find each other and scatter out, so that reduces the central density, and depending on what the cross-section for that interaction would be, you can lower the densities away from vanilla CDM predictions. More recently, there's a lot of fanfare regarding fuzzy dark matter or wave dark matter, in which we're talking about an ultralight particle where the de Broglie wavelength in a galactic halo could be of order a kiloparsec in size. And so then that itself would suppress structure formation and growth below that scale. And the dark matter density profiles that arise in such models are very different from NFW, canonical NFW profiles, and have this soliton core-like feature that we could go and hunt for. So in that context, it's interesting to go out and look at galaxies, and this is work done by other groups 10 years ago, looking at rotationally supported galaxies that turn out to be, this is a relatively straightforward game to play if you've got a nice rotating galaxy, because you can apply first-year physics and say the centripetal acceleration is equal to gravitational acceleration, and use the circular velocities to infer the mass enclosed within each orbit. When you do that, you can construct an empirical density profile, and by and large, these show not this divergent behavior toward the center, which is represented by the gray plots here, but the data are showing turnovers to approximately uniform density cores, and this leads to what is typically called the core cusp problem. The sorts of galaxies that I study are less luminous than these galaxies, and there are lots of reasons for that. Here are some examples. These are the most luminous galaxies I study, and if you speak in terms of luminosities of the sun, they start at around 10 to the 7 solar luminosities and just get less luminous. And so by the time you're here, you don't really see the galaxy. Every star you see here is most likely from the Milky Way foreground. So it becomes hard even to detect these, even though they're in the Milky Way's neighborhood. One reason to study these things is that because they have so few stars, they're almost entirely dominated by their dark matter component gravitationally. So the ratio of stellar or visible mass to dark mass can be 1% or lower in these things. So they represent the most pristine dark matter halos that we have. Therefore, when you read papers on these objects, it's typical to read in the first paragraph that even the first sentence, dwarf galaxies are ideal laboratories for studying dark matter. And I don't like that sentence or that claim because one of the themes of this talk will be that they are not laboratories at all. They are messy astrophysical objects. So they may be the best thing, the closest thing we have to a laboratory in this game, but they are messy, and that messiness is not trivial. So we have to keep that in mind in tempering our conclusions. Nevertheless, it is fun to play this game of trying to infer the dark matter densities, and particularly how the dark matter density varies with distance from the center of these things. And there's a number of different ways you can do this. First, I'll mention a couple that are very clever that I had nothing to do with and have been around for a few decades. Scott Tremaine, author of the Galactic Dynamics textbook, pointed out in the 70s that if you look at this particular galaxy, Fornax, which has 5 of its own globular clusters, kind of hard to make out on this screen. I think that is one, that is one. But globular clusters are smaller in scale than this and contain 10 to the 5-ish stars that are themselves gravitationally bound. But here they're orbiting around Fornax. And Tremaine pointed out that because of all of these things orbiting in a sea of dark matter, you would expect that the interactions, the gravitational interaction of a massive object moving through a sea of dark matter particles would result in a kind of drag force as a gravitational wake builds up behind the object. And this is called dynamical friction. And like friction, it's dissipative, so you should expect in those circumstances, the orbits of clusters or massive objects to decay toward the center. And the observation is that they are not found in the center. So one way of explaining that here is that Fornax has a dark matter halo that does not have an NFW cusp. Instead, it has been shown that if you have a uniform density core of dark matter, that orbital decay tends to stall at about the radius containing half of the stars. And that's by and large where Fornax's globular clusters are found. So that's the kind of argument we're talking about here, a very indirect argument, nevertheless one that gives an interesting result here. A different kind of argument, another indirect kind of argument, has to do with very loosely bound substructure within different dwarf galaxies. You can see a star cluster here near the center of a recently discovered galaxy called Eridanus 2. Here, we can't see it, but there's a star cluster located over here somewhere. And it has been pointed out that just through tidal interactions, if these objects are orbiting in an NFW cuspy profile, those tidal interactions are much more efficient and should destroy such loosely bound substructure. So again, their survival is an indirect piece of evidence for a uniform density core in these objects. In that context, I try to do this dynamically, that is, go to the telescope and look at these objects on the sky, measure the positions and speeds of their stars, effectively the kinetic energies of the stars, and use dynamics to make an inference about the gravitational potential required to keep these objects in dynamical equilibrium, which is something we assume here. So the setup we have is the Magellan telescopes in Chile, specifically that one, the Clay telescope. It's a 6.5 meter mirror. And we have a fiber optic spectrograph where we're plugging fiber optic cables into the focal surface with holes drilled in this plug plate at the precise positions of stars we wish to observe. And fibers carry the light to the spectrograph, which disperses onto the detector. So here we're seeing individual spectra for individual stars. And the features you can see here are absorption due to the presence of magnesium, in this case, in the atmospheres of these stars. That those magnesium atoms are absorbing photons that are emitted at lower depths. And so you see these dark features. But that carries the information that we want to turn into dynamics. So plotting these as photons collected versus energy, this is what we get. And I've spent a lot of my early years at Carnegie Mellon developing this model for fitting these spectra. And it's a model that is fitting not only for the shift, the redshift of these spectra, but also for the chemical composition of the stars. What is the preponderance of iron and magnesium in the atmosphere? What is the mass of the star? What is the temperature of the star? And all of those things affect the features we see here. We can make that explicit by comparing the top left to the top right. Everything on the left is a member of the dwarf galaxy we were observing here, or hoping to observe here. And you can see that the magnesium lines over here are much narrower and less pronounced than their counterparts over here at these wavelengths. These stars are foreground Milky Way stars. They're higher in metal content, so they have more magnesium, so you have more absorption there. They're also lower sizes and stronger surface gravities. That also affects the strengths of the magnesium lines. So the spectra are telling us more than just the dynamics of the stars. They're also telling us about the status of the stars as members of the dwarf galaxy or foreground contamination. And that's important because ultimately I'm trying to figure out what this curve looks like intrinsically inside the dwarf. This is the distribution of redshifts or line of sight velocities that we're trying to measure, because the square of this, the standard deviation, or the width of this curve squared, is directly proportional to the mass of the galaxy dynamically. The problem is, this is not something we observe directly. Instead, there are all kinds of complications added on to this. The first argument that these are messy, not laboratories. The first could be these things might not be, they could have a net rotation, or there could be a velocity gradient that we're observing, and that will have the effect of smearing out this intrinsic distribution. Another effect could be that the stars that we're observing could have low mass and undetectable companions and exist in binary systems. And because binary systems do this, the line of sight velocity we measure will have this component added on top of the center of mass velocity of the binary system. We only care about the center of mass velocity. The binary motion is not telling us about the internal gravitational potential of the dwarf galaxy. It's telling us about the binary system. So that kind of motion adds a background on here. Then we have observational errors. These are very cold systems. So the intrinsic curve we're trying to measure is often competing with the resolution limit of our spectrograph. And that puts us in a dangerous regime. And then finally, we have sampling error. In the worst cases, we don't detect any stars when we go to the spectrograph. In some cases, we're detecting a 3, 4, 5. And so from that, we're trying to make inference about the intrinsic distribution. So if I just put in small n statistics for each of these effects, that's the kind of thing I have to work with. But then on top of that, you've got foreground contamination. So you need to go from this to inferring what that black curve is intrinsically. And all of that is to make the point that this is fundamentally a statistical exercise, this kind of inference. These are the kinds of data sets we have. Information we have is position on the sky. That's just two-dimensional. We don't resolve internal distance differences between the stars. We have what comes from the spectroscopy. So as a function of distance from the center in projection, we have a line of sight velocity. We have a metal content And that's what I have over here. Here you're seeing the member stars in one particular dwarf galaxy. They cluster into a narrow velocity distribution because this is low mass, and it's the square of this width that's proportional to the mass. Everything out here is from the Milky Way, much higher mass, much larger spread here. But this chemical information helps us to decide what the bona fide members of this thing are, especially out here. The members are lower in metal content compared to the relatively evolved Milky Way. So I use all of this information, also the closer you are to the center, the more likely you are to be a member, to decide who the members are and ultimately use that cleaner sample to make these inferences. So going back several years now, we developed a statistical machinery to analyze this kind of sample. And for 2 different galaxies, we came up with the inference that they don't have NFW cusps. The data were best described by uniform density cores. I won't get into the method we used here, but suffice it to say, hopefully suffice it to say, we analyzed 2 different stellar populations in each dwarf and measured the dynamical mass of each and plotted that in this curve and found that this slope was well described by a uniform density core, but not an NFW cusp. I can talk about that later if you like. Now, in more recent times, again, we can apply some novel arguments to some very extreme objects that have been found just recently, within the past year or two, to convince ourselves that, at least right now, they don't live inside canonical NFW cold dark matter halos. So here's observational progress in just the detection of Milky Way satellites. As a function of year, this is the cumulative number of known satellites. And this is since the Sloan Digital Sky Survey gave us this first batch. And now we're into the dark energy survey era, which has increased the numbers dramatically. So it'll be exciting to see where this goes. But we have a lot of objects now, and this is starting to populate regions of rare occurrence in parameter space. So I'll focus on this new guy that was discovered about 6 months ago by the Cambridge group, student, or postdoc now, Gabriele Torrealba. This object is in the constellation Antlia, so it's called Antlia 2. It's the second object to be found in that constellation. And what's interesting about this object, first, is that it's the first galaxy and the only galaxy so far to be discovered in the space of proper motion, which is the tangential velocity components as measured on the sky. This is a very difficult thing to measure because rather than Doppler effect giving you a redshift, to measure these components of the motion, you need to take a picture, wait, and take another picture and see where things moved in angle on the sky. So you have to wait a long time or have a very high precision angular measurement. And the Gaia spacecraft that's still taking data now gives us high precision angular measurements. And so they released their first catalog of these motions in April, I want to say. And right away, this object popped up in the space of proper motion measurements. It's an overdensity right here. And the reason it wasn't spotted before is that it is extremely diffuse on the sky. For its number of stars, it is gigantic. If you're familiar with the Large Magellanic Cloud, which is the most luminous of the Milky Way's satellites, this has the same size as that thing, but it has 5 orders of magnitude less stellar mass. So there was no way this thing could have been found just by counting stars, looking for overdensities of stars on the sky. But because its stars move coherently across the sky, that's how it showed up. So this panel here is making that point explicit. This is luminosity or number of stars in objects versus their size. Everything over here is a globular cluster. They don't really show evidence for dark matter, but mostly because they're small. Dwarf galaxies and all galaxies live over here. These objects, we're not really sure what their status is. They're in this ambiguous transition region. But these lines here are lines of constant diffuseness or surface density. Antlia 2 is way lower in that regard than anything that's been found before. So it's below surface brightness limits up for finding galaxies the usual way. These are its other properties. In terms of its metal content, it's pretty normal for a galaxy of its stellar mass. We have measurements, obviously, of its tangential motions. We went and got spectroscopy to tell us the third component of its velocity. So we have a measurement of its internal kinetic energy, and therefore we can get a dynamical mass. So this is a complicated plot, but I only want to look for now at the top left panel. Here, I'm showing where galaxies might live in the plane of the mass of their halos. And here, everything that's plotted here, every curve plotted there represents one dwarf galaxy. Typically, we cannot infer both the total mass of the halo and the concentration of the dark matter within that halo, or how, I'll just say how concentrated the dark matter is given that mass. So instead, we get a curve for each galaxy in this plane. And because this new object is so large, its kinematics tell us that it has an extremely low density. And that's what's represented here. Its sibling is even more extreme in this particular plot, which is telling us that even though we don't know the concentration and the halo mass simultaneously, no matter what that concentration is, the halo mass is very low. So low, in fact, that it's below the lower limit that is typically ascribed to the conditions that enable galaxy formation. So here, the argument against this thing living in an NFW halo, characteristic of cold dark matter, is that if you force it to live in such a halo, which is completely specified by halo mass and concentration, then you get an absurdity, which is a halo mass that's too low to allow a galaxy to form. So that's the argument. In the other planes, I'm just showing concentration versus size of the galaxy. And in that case here, again, they're very large galaxies. So they're much, much larger than any other galaxy for any possible concentration, given their halo masses. Now, what do we make of this? So given all that I've shown you, everything I've shown you is an argument that the galaxies we've observed don't have the Navarro-Frank-White cusps predicted in numerical simulations of cold dark matter. And that is exciting, and it's tempting then to argue, well, the dark matter must be something else. But since these are messy objects, we have to consider what other explanations there might be. And it turns out that there are plausible astrophysical explanations for these non-NFW behaviors. So the first would be that these objects are orbiting in the tidal field of the Milky Way. So as a result, especially when they come close on non-radial orbits to the center of the Milky Way, they're losing mass to tidal stripping. So the mass that we're inferring now need not represent the mass that the galaxy had when it formed. So that's one way to get out of this absurdity. Yes, it's absurd to have a halo mass of less than 10 to the 8 solar masses, but that's just as a condition for galaxy formation. If you allow this thing to have formed in some higher mass halo, fell into the Milky Way, got tidally stripped, that could explain why now its halo mass is below this value.
What is the galactocentric radius?
Distance from the Milky Way for Antlia 2 is around 100 kiloparsecs, and based on its proper motion, if you assume a vanilla potential for the Milky Way, its pericenter is around 60 kiloparsecs. This guy, Crater 2, which is even more extreme in this argument, has an orbit that's consistent with going through the Milky Way center. So both of these objects are on orbits consistent with having lost significant mass to tides.
Do we know rainfall at 200?
I'm a person who argues that we don't know that, but there are certainly ways to make an inference about that under certain assumptions. Yeah. Here I'm showing what that would be as a function of concentration. But if you want to have a prior on concentration, then you can make an inference like that. over here, I'm showing if you insert a free parameter into the NFW profile that allows for a truncation of the outer halo due to tides, then you get a change in this behavior that allows higher initial halo masses if your tidal truncation radius is eating into where the galaxy lives. So this is just demonstrating that if you allow for tidal truncation, you avoid this absurdity. The other astrophysical complication is, well, these things have formed stars, and the process of star formation releases energy, some of which can be deposited into the dark matter halo and achieve transformation structurally of the dark matter halo. So this is a relatively well-studied process now. The easiest way to think about it is stars form, the most massive of those almost instantaneously for astronomical purposes, explode as supernovae. Those explosions drive out the remaining gas such that at the center where the stars are forming, the gas mass is lost almost instantaneously. So if you're a dark matter particle orbiting near the center in your NFW cusp, and all of a sudden the gas mass disappears inside your orbit naturally expands because it's gained energy. So that's a process of transforming cusps into cores through astrophysical feedback from an astrophysical process. And that's been shown to work in numerical simulations. So we can also account for that process in a simple model where we allow a core to grow, presumably through this mechanism, or alternatively through a self-interacting dark matter mechanism. And if you have a core radius that's sufficiently large, you can also avoid that absurdity and climb above 10 to the 8 solar masses for the initial halo mass. So either of those mechanisms and or their combination can get us out of this mess, out of this inconsistency with expectations under CDM. All right. So I'll turn now to recent work that I did with Justin Reed, who is a dynamicist and simulator working at Surrey in the UK. And he has pointed out something that I think has been overlooked in the recent literature, and that is that we can get meaningful constraints on this core cusp issue without having to do what is a very hard thing, which is measuring the slope of the dark matter density profile. It is relatively easy, by contrast, to measure the mass that's enclosed within some finite radius, so-called half-light radius that contains approximately half of the stars. That's a relatively robustly measured quantity. And Justin's point in this paper is that that can be enough to give us useful information about this problem. Because you can turn such a constraint into the density at some finite radius. Half-light radii for dwarf galaxies tend to be of order 100 parsecs, so somewhere around here and here. Oh, sorry, this is kiloparsecs, so yeah, around here. And the point is, if you can measure the density at that radius, then you can distinguish between NFW profiles and NFW profiles that have become cored and transformed to lower density. Specifically, if you're testing whether a mechanism exists to accomplish this transformation, and you go out and measure a density that's well above this curve, then you know that this hasn't happened. So that's the strategy employed here. And so what we did was consider this idea that you've got core formation that happens not because of an exotic dark matter model, but because of mundane astrophysical processes like star formation feedback dumping energy into the dark matter itself. So what we did was consider a sample of dwarf galaxies that has a range of star formation histories and star formation outcomes in terms of the total stellar mass formed. These are dwarf galaxies ranging from the close companions of the Milky Way here. These are by and large what I've studied. And then some that are a little farther out and tend to have formed stars more continuously over the age of the universe. So across that range of star formation properties, we went and turned to the dynamics and measured this dark matter density enclosed at a fixed radius of 150 parsecs from the center of each galaxy as a compromise where we could get a decent measurement for each galaxy. And here you're seeing Justin's constraints on the dark matter density profiles, but again, the meaningful result is reduced to just a point estimate with an error bar at 150 parsecs in each case. Over here, you're seeing the star formation histories that are available in the literature. So each panel here is containing multiple galaxies of different colors. But the point is you can see the range in star formation histories. This is age, forming stars over much of the age of the universe, as opposed to galaxies that formed stars early on and then quenched their star formation. So if this picture is right, that star formation leads to dynamical transformations of the dark matter halo without needing any exotic physics, then what we should see is those objects that formed lots of stellar mass over much of the age of the universe should have accomplished this transition, and their densities will be lower than those that quenched their star formation early on and formed fewer stars. And that's indeed what we find. So this is showing dark matter density evaluated at that radius of 150 parsecs versus the stellar mass of each galaxy. And if you don't look at the colors of points, you don't see much of a correlation here. But now the colors are telling us about the star formation history. The blue points are objects that formed stars over more or less continuously over the history of the universe, whereas the black points are objects that truncated their star formation early on. And there you see a trend such that these objects have retained high densities, whereas these objects have low densities, and that's consistent with those low densities having been caused by this transformation. You asked about halo masses, total halo masses. Again, I'm not a big fan of pretending we know those, but there are various ways of pretending we do. And Justin has one where he supposes that star formation history is directly proportional to halo mass. And so he used some prescription that he's tested and actually works okay in simulations to turn star formation histories into some inference of halo mass here. And then he's showing if you allow cores to form due to star formation, then you expect those that have formed cores to occupy this blue band, whereas those that didn't stay in this black band. And this plot is showing that if you believe those values of M200 inferred for each dwarf, then in fact you've got the ones that didn't form stars occupying the cuspy region, and those that did hitting the chord region. So what I think we can say about this is not that this proves that the standard CDM picture is correct. What I think it is a consistency check. We didn't have to find that there was this dichotomy. So we could have found that things that formed stars over a Hubble time live up here, or the things that truncated star formation long ago live down here. And both of those would have been problematic for the cold dark matter, the standard cold dark matter model. But that we did find this expected dichotomy is a consistency check that CDM does pass. So I think that's the strongest thing we can say here, that we could have found in this something that very much is a problem for CDM and therefore motivates searching for alternatives in the dark sector. I think we didn't find that here.
Man, you assume that feedback model is correct. You can generate cores in those regions, right? If
Yeah.
the model is not correct, that means that they get the problem.
Well, if the model's not correct, sure. Yeah, I think, and from the discussion we had earlier today, I think the statement that I just made could be applied equally well to SIDM. So in SIDM, I think we agreed that SIDM is perfectly fine with there being this dichotomy as portrayed in both that plot and this plot. So I think that's absolutely true. And my only point is that I don't think this tells us that we need SIDM. It certainly doesn't say SIDM is wrong or that it's not viable. I think it's as viable given these data as CDM. What I would really like to do, though, is I would have loved to find a problem for CDM here, and I don't think this does that at this point. So the reason, again, is that these are messy astrophysical objects. So we don't have necessarily clean tests at this level. So I think we need to get a little bit more clever and look for a cleaner probe of what's going on with the dark matter. And the one place to go is to less messy objects. And galaxies are messy objects, so let's look for the low-mass dark matter halos that need to exist if cold dark matter is correct, but that are so low mass that they never formed galaxies, so you don't have to worry about messy astrophysics. The problem with that, of course, is that these are hard to find. They don't form galaxies, so they're not luminous. So the only signatures they would have, well, one of few signatures they would have are gravitational signatures, so they can be perturbers. So there are a few programs that are being developed to look for these, what I'll call subgalactic dark matter halos. And one of them involves looking for perturbations of strong lenses arcs in strong lenses that would be due to subgalactic dark matter halos viewed in projection along the line of sight to the lens. And that's becoming more sensitive down to the masses of dark matter halos that we're looking for here. So that's promising. There's another idea that is looking for perturbations of the thin stellar streams that are emitted by tidally disrupting objects that are orbiting in the galactic halo. So globular clusters, for example, when they fall near the galactic center, lose streams of stars as tidal tails. If those are being bombarded by subgalactic dark matter halos, that will leave characteristic imprints on that stream in the form of gaps in different velocity structure. So that's another promising route. But the one that I'm hoping to work on in the coming years is yet another probe of these low-mass, invisible dark matter halos. And this would have to do with the survivability of wide binary systems, particularly in the dwarf galaxies, where the density of sub-halos, low-mass dark matter halos, would be relatively high, because these are high-density dark matter systems. And as a result, these should either completely destroy wide binary systems that are loosely gravitationally bound in one passage, or if you're the lowest mass halos, because there are many of them, through relatively nonviolent diffusive encounters that have a cumulative effect over time. And both channels over the age of the universe should truncate the distribution of separations of wide binary stars. There hasn't been much work done on this. This is early work looking at numerical simulations of the disruption of wide binary stars due, actually there's an effect due not only to the substructure, but to the tidal field of the Navarro-Frank-White cusp itself, which presents a very strong tidal field. So this simulation showed that in the tidal field of an NFW halo, the number of wide binary systems declines much more than the number of wide binaries in a core dark matter halo. And you get separations, wide binary separation function is truncated down to much smaller scales in an NFW halo compared to a uniform density halo. So this shows that wide binaries are sensitive to both the NFW versus core cuspness of a halo and the presence of subgalactic dark matter halos. What we don't know is whether wide binaries form in dwarf galaxies. We don't have a good theoretical understanding. But it does remain true that if you look and you find them, you know they do form. And then you also right away know that there are no perturbers in the form of subgalactic dark matter halos, and there's no NFW cusp. Both of those things, to be diagnosed in a very low mass dwarf galaxy, would be monumental achievements and step forwards in our understanding of dark matter on small scales. Yeah?
Excuse me. Does knowing where this turnoff in the distribution function is going to be kind of depend on knowing the total mass of the halo? Is that possible?
The total mass of the halo that's hosting the population of stars that has the wide binaries. That's not so important as just the density of dark matter where the stars are living. It will also dictate what the most massive perturbers are. So the subhalos that have the most catastrophic effect on the wide binaries tend to be the most massive subhalos within the host you're talking about. So in that sense, that will matter.
Oh, I guess okay. I got it.
This, I should also say, this is basically impossible to do right now because you need very exquisite angular resolution to see close pairs, which would be how you find the wide binaries. And HST has that resolution, Hubble Space Telescope has that resolution, but it has a very small field. And to see enough stars to do this, you would have to tile with HST, which is prohibitively expensive. But the WFIRST mission will solve that problem by giving us HST angular resolution over a field that's well matched to get the dwarf galaxies in one snapshot. So this is a very good reason to do WFIRST. And also on the horizon is something that I'm trying to make sure happens. There are a lot of spectroscopic surveys coming up, but very few of them are well matched to analyze the stellar kinematics of Milky Way dwarf galaxies. Either they are on telescopes that are too small to build meaningful statistical samples of the stars in the dwarf galaxies, or their spectral resolution is too low to resolve the internal motions of the dwarf galaxies. So both of those problems would be massively fixed by this effort to turn the CFHT, Canada, France, Hawaii telescope on Mauna Kea into MSE, the Mauna Kea Spectroscopic Explorer, which would turn a 4-meter telescope with some effort and expense into an 11-meter telescope, which would be used for spectroscopic surveys that would have 4,000 fibers observing over a degree field, so wide field, massively multiplexed, many fibers with big glass. And it would also offer a range of spectral resolutions, ranging from low resolutions, good for extragalactic work, to high resolution, good for planet detection, certainly my work, et cetera. So this is an effort that's getting going now, and I'll just say I endorse it. So finally, I'll summarize by harping on my theme that dwarf galaxies are perhaps one of the better probes we have of the nature of dark matter, but they're not laboratories, and so there's some nuance here, and we have to treat these as the messy astrophysical systems that they are. There are several dwarf galaxies, by and large, that are showing evidence against the NFW profiles that I think naively we've expected to exist if there's classical or canonical cold dark matter. We do have new information coming from correlations between star formation histories and dark matter densities that we're measuring in some of these systems. So there's a challenge now for the non-standard CDM models to be compatible with those same observations. And I think I agree with Haibo that SIDM passes that test for now. It remains to be seen whether things like fuzzy dark matter would naturally expect that. But there's a new challenge for both observers and theorists, and that's to come up with clever new tests that give us a cleaner probe of the nature of dark matter on small scales. And I think the best way, or one promising way to do that, is to look for subgalactic dark matter halos, however we can find them. So with that, I'll stop and thank you, and I'm happy to answer any questions.
Yeah, Matt, in terms of the two sets of galaxies with different star formation histories, do those also, are they distinguishable in terms of their phase space of position and velocity relative to the galactics?
They are. That was here. Oh. They are. The low density things that have constant star formation, or more constant star formation history, tend to be farther from the Milky Way, and notably, they also tend to be more rotationally supported. So we're getting the densities here from rotation curves, as opposed to this weird statistical analysis. So that's actually a place to poke on this result, because these are, we have this systematic offset, but these are also systematically different systems that are analyzed in a different way. So it remains possible that there's a systematic here that's due to difference in analysis. There is one object that belongs to that's close to the Milky Way. I can't read the text here, but one of these objects is close into the Milky Way and is supported by random motions. So there is some mitigation of that problem.
To go from here to the next one where you have had a core, because
Yeah.
you have only one point, you have to be assuming some priors on the halo mass. So now, the ones that are quenched means that they stop forming stars. So did you consider the possibility that they are in more massive plasmatic halos, but they just were stopped? They couldn't achieve the real mass that they were supposed to have because they were quenched. Whereas the other ones continue working with their stellar mass all the way to the zero. So this could be just a halo mass.
Yeah, let me explain how this axis came. So you're right. You have to suppose something about the halo mass, and what was done to get this halo mass, the x-axis for each dwarf, was explicitly tied to the star formation. That's just how Justin decided to do this. He's got some abundance matching scheme that relates star formation history to halo mass. So that's how that was done here. I don't know if that answers your question, or
I'm just saying
how
the
that,
ones that are cusp,
yeah.
they could be equally a core if you place them in a more massive.
Ah, yeah, yeah. That's actually,
But I'm not sure how much you would need to shift.
yeah, I kept making this point to Justin many, many times, that since we just have a point estimate of the mass, you can always say, maybe that's something to show here. So if you measure a density that's here, and it's just 1 point, you could argue that that's a core, and the rest of the profile goes like this, right? And you can't say anything is wrong with that. And that's why I think all we have is a consistency check here. We're not even able to say that these things, the dense things, live in. We haven't proved that they live in cusps. It's just consistent with their high densities are consistent with cusps. If they live in cores, the constraint becomes that they have to be very dense cores. Yeah, I think that's absolutely right. Yeah.
It's a better data set than any of the rest of us have.
It means you didn't fake the data.
Yeah, it means it's not fake.
I was just wondering if there was some reason, like it was this is an outlier in some way that you know about. It's just random.
That is Carina. It is an oddball in its stellar populations, not in any way that obviously explains why it should lie where it does here. Perhaps given the magnitude of the error bars here, finding one such point is not a surprise in this plot. Yeah, I think.
I just have a comment on your statement that the dwarf galaxies may not be in the laboratory for exploring darkness. If you think about high energy physics, the larger hadron collider, right? Very massive system, right? Because the hadron collider, to find a helium, it took like 5,000 scientists many years to find a helium particle, right?
Yeah.
So I would say, you know, this in high energy physics, this is as good as that we have. So I think that we'll argue with it.
I guess we're getting into semantics here. I will contend that LHC is much more appropriately termed a laboratory than Fornax, the dwarf galaxy, is. Yeah.
apart from the galaxy you described.
Yeah.
What do you see coming out of Gaia?
Well, the first thing we got was this, a new galaxy. But for just talking about what we learn about objects we've known about for a long time, now that we have Gaia, I presented this as the data that we have. We have position on the sky. We have spectroscopy telling us redshift distribution and metal content, say, of stars. Gaia gives us a whole, at least 3 other dimensions that are useful in these kinds of analysis that I've started to work with but haven't finished anything to the point where I can show it. But we have a 2-dimensional plane of motion that way versus motion this way. And we've already seen how that can help us identify members of a dwarf galaxy and its orbit in the Milky Way. Gaia also measures a parallax, which is triangulation and proportional to the distance to these objects. The dwarf galaxies are sufficiently far away that their mean parallax is 0, so their negative parallax is measured for these things. But that's still useful because the foreground stars have positive parallaxes. So we can use parallax and proper motion from Gaia in these kinds of analyses to clean out the foreground. And ultimately, not yet, but with Gaia, we just need to wait a little longer to resolve the internal transverse motions inside the dwarfs. Right now, they're unresolved, but eventually that will be a game changer for at least a few systems. Yes, for us to divinate.
Well, that was great. Thank you very much.
Yeah, thanks, Steve.